안녕하세요, 로얄아이비 제이퍼 강사입니다. So this question's focused on complete combustion of an organic compound called menthol. Complete combustion of menthol produces 0.4490 grams of carbon dioxide and 0.1840 grams of water. Now, since complete combustion produces only carbon dioxide and water, all of the carbon in menthol is then contained in the 0.4490 grams of carbon dioxide, and all of the hydrogen is in the 0.1840 grams of water. And so for us to find the empirical formula, since we need the number of moles of carbon, hydrogen, and oxygen, we're first going to find the number of moles of carbon and hydrogen. And then using the mass of these moles, we're going to try and identify the mass of oxygen. So first, to find the molar mass of carbon dioxide, we add 12.01 to twice that molar mass of oxygen, which is 16, and that gives us a molar mass of 44.01. Now for the molar mass of water, we multiply the molar mass of hydrogen, which is 1.01 times 2, plus 16, and that gives us 18.02. Then using these molar masses, we're now going to calculate the number of moles of CO2. The number of moles of CO2 is 0.4490, the given mass, divided by the molar mass, which is 44.01, which gives us the number of moles of CO2 as 0.01020 moles. We do the same for water. Now, to find the number of moles of water, we do the same. We divide the given mass, which is 0.1840 grams of water, by the molar mass of water, which is 18.02. Okay, now that gives us 0.01021, but there's 2 hydrogens in water molecules, so we multiply that by 2, which ultimately gives us a number of moles of 0.02042 moles. Now, since we have the moles now, we're now going to take those moles and multiply by the molar mass of carbon and hydrogen each to figure out the mass of carbon and hydrogen in the menthol. So we multiply carbon's moles, which is 0.01020, by the molar mass, 12.01, and that gets us 0.1225 grams. That's the amount of carbon in menthol. Now, to find the mass of hydrogen, we multiply the 0.02042 moles by the molar mass of hydrogen, which is 1.01. And that gives us the mass of hydrogen as 0.02062 grams. Now then, since we need to find the number of moles of oxygen, we have to now then calculate the mass of oxygen contained in the 0.159 grams of menthol. And we can do that by subtracting the mass of carbon and hydrogen from the original mass. So it's 0.1595 grams minus 0.1225 grams, which is of the carbon, added to the mass of hydrogen, 0.0206 grams of hydrogen. And when we input this, we get the mass of oxygen as 0.0164 grams. Now, with the mass of oxygen found, we're now going to find the number of moles of oxygen by dividing 0.0164 by the molar mass, which is 16.00 grams per mole. And that's going to give us the number of moles of oxygen as 0.001025. Now, to find the empirical formula then, you need to find the ratio of carbon, hydrogen to oxygen. And we do that by dividing the number of moles for each element that we found by the lowest number of moles, which is 0.001025, the number of moles for oxygen. And when we input that in, we're going to get a ratio of roughly 10 carbon to 20 hydrogen and 1 oxygen. And so then that will wrap up our empirical formula for menthol as C10H20O. Now for the second equation, they ask us to find the molar mass of menthol. The data that we're given is that we have 0.150 grams of menthol, which when vaporized gives us a volume of 0.0337 decimeters cubed at the temperature of 150 degrees Celsius, and pressure is given as 100.2 kilopascals. For this question, we're going to use a couple of equations. First, we need PV equals to nRT, which is our ideal gas equation. And from this, we're going to isolate N, because we need the number of moles to eventually get to molar mass. So then N will become PV divided by RT. Now for this equation, we need pressure in pascals. So we multiply the 100.2 by 1,000. And then we divide the volume given, 0.0337, by 1,000. And so the thousands cancel out, which makes calculation a little bit easier here. Then we're going to divide this by R, 8.31. This is given in your data booklet. By the temperature, which is 150 plus 273, because temperature has to be in kelvins. And then this gives us the value of 0.00096. That's the number of moles. With the number of moles of 0.00096, we can find the molar mass now using the mass given. So molar mass can be found by dividing the mass that we're given, 0.150 grams, by the number of moles that we found, which is 0.00096. The molar mass of menthol can be found by dividing the mass given, 0.150 grams, by the number of moles, 0.00096 moles. And that's going to give us the molar mass of 156 grams per mole. And so that's our molar mass of menthol. So the third question focuses on the molecular formula. And so here they ask us to find the molecular formula of menthol using our empirical formula and the molar mass we just found. Now to do that, we need factor x, and x is what we're going to multiply the entire empirical formula by to figure out the molecular formula. Now to do that, we divide the mass of the molecular formula by the mass of the empirical formula. And so the equation goes, x is equal to mass of the molecular formula divided by the mass of the empirical formula. Now, in this case, our mass of molecular formula is our molar mass, which is 156. We need to find the mass of the empirical formula, which was C10H20O. So then 12.01 times 10 plus 1.01 times 20 plus 16. And so that's actually going to give us 156 divided by 156.3. So roughly 1. And so therefore, the molecular formula for menthol is not any different to its empirical formula. And the molecular formula that we just worked out is C10H20O. Now for this question, we're going to focus on an ester. And so they tell us there's an ester compound that contains carbon, hydrogen, and oxygen, just like every other organic compound. And here they say when it's completely combusted, there is 6.93 times 10 to the power minus 3 grams of carbon dioxide and 2.83 times 10 to the power minus 3 grams of water produced. Since complete combustion only produces carbon dioxide and water, we're going to work this question just the same way as we did the previous one. So first we're going to find the number of moles of carbon by dividing the mass of CO2 given, 6.93 times 10 to the power minus 3 grams, by the molar mass of CO2, which we worked out previously, 44.01. And that's going to give us the number of moles as 0.000157. Now we find the number of moles of hydrogen the same way. And so we're going to divide the mass given to us, 2.83 times 10 to the power minus 3 grams of water, by the molar mass of water, which is 18.02. Now remember, we need to multiply this by 2. And so when we get 0.000, now with the number of moles of carbon and hydrogen found, we now find the masses of carbon, 0.00157 times 12.01, which gets us the mass of 0.00189 grams. Now the mass of hydrogen can be found the same way. We multiply the number of moles of hydrogen by the molar mass of hydrogen. And so we multiply 0.000314 by 1.01. And that's going to give us the mass of 0.000317. Now, with the mass of carbon and hydrogen found, we can then calculate the mass of oxygen by subtracting the mass of carbon and hydrogen, 0.00189 and 0.000317, from the mass given, which was 3.00 times 10 to the power minus 3. Now, when we input that in, we get the mass of oxygen as 0.000797 grams. Now, we're going to use that then to find the number of moles now. And it'll be 0.000797 divided by 16, the molar mass of oxygen. And that's going to get us the number of moles as 0.0000498. Now, we then need to find the ratios of carbon, hydrogen, and oxygen, and so we use the number of moles that we found for carbon, hydrogen, and oxygen, and we're going to divide by the lowest moles, which also happens to be, in this case, that for oxygen. And so we're going to divide everything by 0.0000498. Now, we're not going to get a whole number in this case as well. And so when you input that in, the value that you get for carbon happens to be 3.1, and hydrogen gives you roughly about 6.3, oxygen is 1, and so your empirical formula turns out to be C6H6O. And so to find factor X, we're going to divide the mass of the molecular formula by that of the empirical formula. And so that would be 116.18 grams divided by the mass of the empirical formula, which was C3H6O. So then we multiply 12.01, the mass of carbon, times 3 plus 1.01 times 6 plus 16. And that's going to give us 116.18 divided by 58.09, which will roughly give us 2. And so then we multiply everything in the empirical formula by a factor of 2. And so we're going to get C6H12O2 as the final molecular formula for this question. Today, we're going to look at a stoichiometry question from the recent 2021 May exam. So first, we start off by looking at decomposition of calcium carbonate using heat into calcium oxide and carbon dioxide. For A, they want us to calculate the volume of CO2 produced at STP when 555 grams of calcium carbonate decomposes. So first, what we need to find is the molar mass of calcium carbonate so that we can calculate the number of moles of calcium carbonate. And so the molar mass of CaCO3 is equal to the molar mass of calcium plus the molar mass of carbon plus the molar mass of 3 oxygens. And that's going to give us 100.09 grams per mole. Now, with the molar mass, we can find the number of moles of calcium carbonate, which would be 555 grams divided by the molar mass, which is 100.09 grams per mole. Okay, and that gives us 5.55 moles. Now, when you look at the ratio of calcium carbonate to CO2, you can see that it's 1:1. And so therefore, the number of moles of CO2 that we can make out of 555 grams of calcium carbonate is also 5.55 moles. Now then we can convert this into volume using the molar volume of gases, which is 22.7 decimeters cubed at STP. We're already told that the condition is at STP, so all we do is multiply the number of moles found by the molar volume, which is 22.7 decimeters cubed per mole. And that gives us the volume of 126 decimeters cubed. So that's how much CO2 we can make from 555 grams of calcium carbonate. For B, they give us the data regarding enthalpy and entropy for calcium carbonate, CaO, as well as carbon dioxide. And so in B1, they want us to calculate the enthalpy change of the reaction in kilojoules for the decomposition of calcium carbonate. And so here we know that enthalpy of reaction is equal to the enthalpy change of products minus the enthalpy change of reactants. And so here we have negative 393 for CO2, 0.5, okay, plus that for calcium oxide. And we're going to subtract the one for your reactant, which is $1,207 for calcium carbonate. And so here what you get is when you input all this in, you actually get a positive number. So we kind of want to keep that positive sign because that shows us that it's an endothermic reaction. And so it gives us 179 positive kilojoules. So that positive sign shows you that it's an endothermic reaction. Then they want us to calculate the change in entropy, and so we're going to use the same format of the equation. We say entropy change for the reaction is equal to entropy change for the products minus the entropy change for the reactants. And so we have 214 plus 40. I want to subtract that from, so we subtract 93 from 214 and 40, and so we get a positive value of 161 joules per Kelvin per mole. And so for part 3 of B, they want us to find the temperature at which calcium carbonate decomposes spontaneously. And so remember, for spontaneous decomposition, we need Gibbs free energy to be less than 0. The equation that relates Gibbs to enthalpy and entropy is the one that says Gibbs change in Gibbs will be equal to the change in enthalpy minus temperature times the change in entropy. And so when we take these two and formulate an equation that will help us identify the temperature, we get enthalpy change minus temperature times entropy change should be less than 0. Now we plug in the values. Remember that enthalpy and entropy were in different units. So this is kilojoules per mole minus temperature times the change in entropy, which is 161 joules per Kelvin per mole. And so already we have the difference in units. We're going to change them to the same units. So we're going to keep the kilojoules. And to convert the joules into kilojoules, we're now going to divide this by 1,000. And so we get 179 minus temperature times 0.161 is less than 0. Now isolate T. And then divide by that minus sign, which will flip that sign there, and you get temperature actually has to be greater than 1,112 kelvins for this reaction to become spontaneous. And when you actually sit and think about this logically, you know that calcium carbonate is very stable in the lab. And so it makes sense that you'll need a really high temperature because 1,102 Kelvin is a significantly high temperature for the decomposition of calcium carbonate to occur spontaneously without any input of energy. Lastly, they want us to calculate percentage yield of calcium carbonate given that the amount collected in the experiment was 2.85 grams. Now remember, percent yield is equal to the actual mass formed divided by the theoretical, which is basically what you calculated, times 100%. And so that's 2.85 divided by 3.3, which is what we calculated in the previous question, times 100%. And so here we get 85.6%. That brings us to the end of this little mini lecture. Thank you for watching.